Hi everyone, welcome to this talk. Today's speaker is Ava Amini. Ava is a senior researcher in the biomedical machine learning group at Microsoft Research, New England. Her research focuses on developing new computational solutions for problems critical to precision medicine, where she worked at the intersection of machine learning, biophysics, and cancer biology. She completed her PhD in biophysics at Harvard University and her bachelor degree in computer science and molecular biology at MIT. In addition to her research, she is passionate about machine learning outreach and leadership, and is the lead organizer and the instructor at the MIT Introduction to Deep Learning, as well as co-founder of Momentum AI, which provides all expense paid program for high schoolers to learn AI. Thank you so much, Ava, for accepting our invitation and looking forward to the talk.
Thank you so much, Prudencio, for the kind introduction and for the invitation to speak in this seminar series. I'm really excited to be here and have this time with you all. So as Prudencio mentioned, my name is Ava. I'm a researcher at Microsoft Research New England. And today in this talk, I'm very excited to share with you some of our very recent work in exploring how we can bridge computation and experimentation, specifically in the context of molecular modeling and drug discovery, using novel methods for uncertainty estimation in machine learning. So I'd like to begin by taking a broader view before we dive into it and considering a few exemplary areas in medicine and biology in which we're already seeing that machine learning is poised to make a truly transformative impact. And as you know, and as we've already seen, machine learning has shown tremendous promise in its ability and its potential to help us diagnose disease, for example, through automated analyses of medical images like CT scans or MRIs, to be able to understand fundamental biology at the molecular scale, as is the case in protein structure prediction and protein function modeling, and even to generatively design new therapeutics or to discover novel compounds that can be deployed for therapeutic applications. And two prominent works that have highlighted this have been in the case of antibiotic discovery looking at small molecules, or even in the design of improved gene therapies through protein engineering. However, in all three of these cases and these application areas, even as machine learning and deep learning approaches continue to develop and mature and move closer and closer to deployment, they're fundamentally unified and built on this requirement for experimental data and experimental validation, or even clinical validation. And that's something that is, I think, particularly prominent in the biological and chemical sciences, is that so much of our current pipelines and the way we actually move things closer to translation is driven by human beings and by physical experimentation. And I think that's the reasons for that are twofold. Firstly, because the data that we need to train these algorithms is largely experimentally generated. And secondly, because in order to deploy machine learning and computational solutions for these purposes and for these applications, we ultimately will need experimental or clinical validation of any in silico predictions that our models may make. And so these are really fundamental steps of this discovery pipeline that at best can be automated, but are difficult to automate. And critically, these studies take tremendous costs and resources, whether it's in terms of personnel, material requirements, monetary investment. And so I think this raises this broader question of whether or not we can actually not only use computation to accelerate the predictive process, but whether we can leverage computation to try to intelligently inform and guide the experimental discovery and experimental modeling process itself, and therefore try to bridge this gap. To make this more concrete, we typically think of experimentation as the means by which we make measurements of a chemical or biological system. For example, of small molecules activity in killing a particular bacterial strain. And it's this measurement process that in turn generates data on which we can then train our computational models to, let's say, predict a target property or a label of interest. But as we know, right, these models are only going to be as good as the data they see, which in these use cases is difficult, costly to collect. And what this means in terms of the model's performance itself is that it can now be susceptible to failures on out-of-distribution regions. And furthermore, these models traditionally do not provide feedback back to the experimentalists on what questions or regions of a data landscape or an experimental landscape could even be worthwhile to investigate. And so there's this tremendous need for how we can design new algorithmic approaches that can actually address these problems head on in order to now inform the downstream experimental process. And I hypothesize, and as I'll share in the talk today, that methods for uncertainty quantification in machine learning and deep learning have a tremendous potential to do exactly this. And that's because uncertainty fundamentally gives us this notion on regions or instances of the data landscape and the predictive landscape in which a model may need more information. And therefore, these algorithms that can quantify this notion of predictive uncertainty could potentially help us focus experiments on hypotheses that we're more confident in, that may have a greater likelihood of experimental success, or even to facilitate the exploration of new data regions in which models may have greater uncertainty. And this is particularly important, just to really drive this point home, when the data acquisition process is slow and labor intensive and costly, as is the case in much of biomedicine, but I think particularly relevant and prominent in the drug discovery and molecular discovery pipeline. And so to really highlight that and to highlight the specific use case that has brought us all together here, in molecular discovery, a fundamental goal is to try to identify promising molecular candidates, whether they be therapeutics or materials, that have specific properties that we are seeking to design around or to exploit for a particular downstream application, right? Ranging from antibiotics and targeted therapies for cancer and other diseases to engineering material-based devices for industrial applications. And so we're interested, right, as computational-minded folks, in ways we can use algorithms and computation to accelerate this process. And this is particularly true in the context of therapeutic discovery, right, where the standard path to FDA approval for an average drug is extremely time-intensive and takes over billions of dollars of monetary investment. And as a result of this, I think it goes without saying that machine learning has been increasingly applied to this end in the specific context of trying to predict various functional properties directly from molecular structures, right? And this is this idea of mapping and learning structure-activity relationships in the molecular science, whereby we start with some molecular structure. Our goal is to predict a target property of interest. And in addition to the overall excitement that recent approaches in this field have garnered in the computer science community, this has also been spurred on by highly relevant predictive tasks in chemistry, drug discovery, and biology and physics, ranging from bioactivity prediction of dosing and dose response curves, to modeling quantum mechanical properties and binding pocket or protein small molecule interactions, just to name a few. And as a result of this reciprocal process, there's been tremendous development from both the fundamental side as well as the application side. And yet, what machine learning and artificial intelligence for molecular discovery then affords us is a toolkit by which we can now start to think about how we can actually navigate the vastness of chemical space. What do we mean by navigate? Here, specifically in this context, I'm referring to the notion and the ability of being able to intelligently prioritize compounds for downstream validation or for deployment in a particular application. And for this task of compound prioritization, it's insufficient just to have a model that works well in predicting a target property as well. Ultimately, we want our models to confer to us a sense of when we can actually trust their predictions, if our goal is to ultimately take these predictions and move them forward to experimental validation. And it's this use case that I think really highlights why this paradigm of this interplay between experimentation and computation becomes so important, motivating this sense of using uncertainty to actually guide the experimental process itself. Okay, so at this point, hopefully I've motivated strongly enough that uncertainty can be a potential approach to bridge this gap and facilitate this interplay. That being said, as you may be aware, several uncertainty quantification methods have recently been developed in machine learning and deep learning, and yet there has been a tremendous lack of consensus on what is the quote unquote best uncertainty quantification method to use in the context of molecular modeling and molecular discovery. To that end, a couple of years ago, a study from our collaborator Connor Coley's group kind of systematically compared and benchmarked different uncertainty quantification methods on a number of different data sets and tasks in the context of molecular modeling. And what this analysis showed is overall that there was a startling lack of consensus on what was the most performant method across these various data sets. And the plot that I'm showing you on the right is a pairwise comparison of all the different uncertainty quantification methods that were benchmarked in this study on a particular data set of interest. And what the green color shows you is that one particular method, the primary estimator on the y-axis, outperforms the secondary estimator on the x-axis. What you may notice is that at the top row here, we have an ensembling method, right? This is an ensemble of the message passing graph neural network. And as you probably can appreciate on this particular data set, ensembling performs quite well. But the fact is that this ensembling method, which is largely the gold standard uncertainty quantification method for deep learning models, does still face significant drawbacks. Namely that there's this requirement to train multiple independent models and run multiple forward passes through those trained models, which in turn becomes computationally expensive as you move towards large data regimes or situations in which you want to run expensive simulations or perform active learning, or any context in which the model may require more computational resources to train. So we have this limitation of ensembling with respect to the computational cost. Lastly, I also want to call attention to the fact that you may notice that there's an additional very prominent green row here, which corresponds to mean variance estimation, which is also highly strongly performing on this particular data set. However, that method focuses exclusively on this notion of data uncertainty. We are unable to estimate the predictive or model uncertainty directly using that approach. And so these two seminal limitations with respect to the computational cost of ensembling and the limitations of current data uncertainty estimation methods motivated us to ask whether or not we could develop a method, a new algorithmic approach to better estimate model or epistemic uncertainty directly, by which we could create a new approach that could operate at no additional computational cost to the network, alleviating the need that ensembling presents to train multiple independent models or sample from a model multiple independent times in order to get a predictive model uncertainty estimate. And so today, in today's talk, I will share our work in developing that method, which we call evidential deep learning, which achieves uncertainty-aware molecular modeling at no additional cost in the context of neural network approaches. So first, I'll go through the details of the method and showcase how we are able to deploy it for molecular property prediction. And then I'll focus the bulk of the talk on discussing two ways in which we can leverage this method to now use our predictive uncertainties to accelerate experimental pipelines in drug discovery. Firstly, by leveraging evidential uncertainties in the context of active learning, where we show that our method can achieve efficient experimental labeling in molecular discovery. And thirdly, in closing, I'll show how we can now actually deploy these uncertainties at deployment time to actually accelerate the experimental discovery process by targeting virtual screens towards high confidence therapeutic candidates. Take a sip of water before continuing further. Okay, so to dive into it, we're going to begin by exploring this uncertainty quantification method, which we call evidential deep learning. What we specifically did was develop an algorithm that allows us to develop uncertainty-aware neural models of small molecule structures, where we can now leverage any representation learning framework, for example, a message passing graph neural network, and incorporate our evidential uncertainty algorithm to not only learn to predict a target property of interest, but also to model the underlying evidence in support of that prediction. And this, which we call the evidential distribution, allows us to directly estimate predictive uncertainties without the need for ensembling or sampling. So to get into the details of how this method works, as I kind of introduced, the majority of uncertainty quantification approaches for deep learning models use this notion of sampling to obtain many predictions from a model to then generate an estimate of model uncertainty. And conceptually, the way we can think of this is by having an ensemble of models, right? And so as we step through our ensemble, right, we're obtaining a single prediction from each member of our ensemble. And that prediction is going to fall somewhere on our predictive output space, which I'm visualizing here on the right. And we can do this multiple times, sampling and training these multiple models that constitute our ensemble, repeating this process to generate this set of predictions. Now, to estimate the epistemic uncertainty, or that model uncertainty that reflects our confidence in the prediction itself, all we need to do is look at these samples and then compute the variance across these predictions. And as you know, if we get a large variance, this tells us the model is in disagreement across these samples, therefore having high uncertainty. And on the other hand, if the samples are very close to each other, the variance is small, telling us we have a very confident prediction. Now, as you can appreciate, this is computationally expensive, right? In the schematic that I'm showing, each of these models is independently trained. And we need all these individual samples and run our training and forward pass through each of these models to generate this estimate. However, what we're really caring about when we consider this depiction is not what the actual samples themselves are, but rather the variance across them. And in reality, these samples are being drawn from some underlying distribution, which is what we're trying to approximate via this sampling approach. So we ask whether we can directly obtain and parameterize the statistics of this distribution such that we alleviate the need for sampling and be able to directly and analytically compute a fast, calibrated metric of uncertainty without this need for sampling. Put simply, to directly learn the parameters defining this likelihood distribution that I'm depicting on the right. And that's the heart of the evidential deep learning approach, which tackles this problem of uncertainty estimation by treating learning as an evidence acquisition process. What this means is that instead of predicting the target of our problem alone, for example, a molecular property, we train and formulate a model to now learn a full higher order evidential distribution on top of this prediction, capturing the associated evidence that comes with the predictive output itself. The way we achieve this is by training our neural network model to output the parameters of these evidential distributions through a two-component objective that focuses on both maximizing the model's fit to the data, and secondly, jointly minimizing its evidence in instances when the model makes an error. And so concretely, we can see how well our evidential learning approach functions on a simple learning problem, where we see this instance where we have trained a network using data between -4 and 4. Predictions are aligning well, uncertainty is low, but now we see that the model starts to fail on these out of distribution regions beyond the training set and significantly incurs greater uncertainties in these out of distribution regions. I'll pause momentarily because I think I saw a hand raised, but I very well could have missed it.
Yes. So if we go quickly back to the previous slide,
Yes.
can you maybe explain why you choose kind of as a prior for the standard deviation, a gamma distribution, why you choose a normal prior for the mean?
Yes. Yeah. So that's very well taken out, right? As you pointed out, we are assuming that our data is drawn from a normal distribution, and therefore that we can place this higher order distributional prior, which amounts to a normal inverse gamma. And the reasoning for that is that by placing the normal prior, we can formulate the evidential distribution according to the conjugate prior of the normal distribution. And therefore, if we had chosen a different prior other than a normal, the form of this higher order evidential distribution would be according to the conjugate prior of that underlying data distribution. And similarly, right, a way you can also understand this is in the case of extension from here, the univariate regression setting to now a multivariate regression setting, where if we assume our data is drawn from a multivariate normal distribution, then our conjugate prior is a normal inverse Wishart distribution, which we have now explored in extensions and new methods that we're developing. But we haven't yet studied distributional data priors that are not normal. And so that's, I think, definitely an opportunity for continued investigation.
Hi. I
Yes.
am kind of confused between the two objectives which you posed, maximize model fit and minimize. It seems they are the same. It's like likelihood and error. So normally in multiple objective, you have contrasting objectives. So can you intuitively tell the differences?
Right. Yeah. So you're right in that this is different from having a contrasting objective. The nomenclature I used in referring to multi-objective amounts to the fact that we have two terms in our loss function itself. One that is a negative likelihood term that captures this notion of model fit, and one that is effectively a regularization term, which captures this notion of minimizing the incorrect evidence. Hopefully that clarifies.
And there's a few more questions in the chat. Do you want to take them now or maybe move for a bit?
I'm happy to take them and then move forward.
Okay. So
Yeah, so the data in point 1 is the training data. Yes. Could you please explain what is the predicted evidence function? I'm not exactly sure what this is referring to. Could you please clarify? Otherwise, we can perhaps have further discussion at the end.
Can I ask a question?
Yes.
Just to clarify on what the method is, so you were trying to sort of bypass the ensembling method in some way. So it's basically saying that if you train different random models, like randomly initialized models, it's going to give you a distribution over predictions, and you want to directly learn that distribution over predictions by bypassing the ensembling. But so this is a Bayesian way of, so you're putting a prior on the parameters, you're fitting the data likelihood, and then you are doing a posterior. And in this case, normal inverse gamma is a conjugate family, so you get a normal distribution as a posterior. In this case, you were still so when I'm saying that the data is still prediction of a model. So I'm assuming that you have a prior over this distribution. You fit a model, collect a data point, and then update a posterior. And then you fit another model, collect that data, and then update your posterior. Is that the process? So it's still a sequential fitting of models. These models are not fit by random initialization. Is that the idea, or?
So, yeah, thanks so much for the question. So I have a slide after this that I think will help clarify. Okay. Firstly, I will raise that the principle is related to the Bayesian neural network type mindset, or the Bayesian learning mindset, but differs notably in that case, right, we're in Bayesian deep learning, you're placing a prior or a distributional prior over the neural network weights themselves. Right. That is not the case with our approach. In our approach, we're considering this higher order evidential prior over the predictive likelihood itself. And so the network itself, it is a single network, and the weights are not defined as distributions. The way that we are able to then achieve the notion of uncertainty is by training the network to directly output these parameters M, which formalize and constitute the parameters of that evidential distribution itself. And what this amounts to in practice is that when we take our input of interest, let's say it's a molecular structure, we train our feature extractor, which is, let's say now in our case, a graph neural network, then we can append a evidential layer as the output head of the network, where now instead of predicting a single output, for example, the predictive mean, we now predict these 4 evidential parameters, these 4 evidential outputs, which parameterize exactly this normal inverse gamma distribution, which in turn allows us to create this full distribution over the parameter mean and variance of the model. And conceptually, this is very similar to the notion of mean variance estimation, right? Where in mean variance estimation, you're predicting both a target mean and a target standard deviation. The difference is that in mean variance estimation, due to the nature of the method, it is restricted to data uncertainty. In our formulation, by parameterizing this higher order evidential distribution, we can now generate epistemic or model uncertainty estimates as well. Formally, how we then extract these uncertainties and extract the prediction itself is by considering the parameters of this higher order normal inverse gamma distribution and the moments of that distribution, which can then in turn define the predictive target, as well as both the aleatoric and epistemic uncertainties. And so hopefully that this slide shows that the evidential uncertainty approach does not require a distributions over the individual network weights, as is the case with Bayesian neural networks, but rather is functions by considering the formulating the outputs of this higher order evidential distribution as the outputs of the neural network itself, incorporating this two-component loss function, which I introduced earlier, and then training the network end-to-end and producing these single-shot estimates of uncertainty based on the evidential parameters themselves. Okay, so this provides the core of the underlying algorithmic methodology. And I'm happy to continue the discussion around the details of our approach in the time for Q&A that we will have at the end. So with this in hand, what we did was take the evidential learning algorithm and design a graph neural network message passing model that functions exactly as is outlined on this slide. And in turn, we took that resulting model and started to build uncertainty-aware molecular property prediction models that we could then train and deploy on a number of different data sets, focusing on a range of different molecular properties, including drug target ligand docking, solubility, free energy, so on and so forth. And in each of these cases, right, with our evidential approach, we are generating both the estimate of the target property itself, as well as focusing primarily on the estimates of the model uncertainty. And our first task was to assess how well these uncertainties performed in the sense of how calibrated they were to prediction errors. And encouragingly, we observed that when the evidential method was most confident, associated with lower uncertainties, this correlated with lower predictive errors, as we're seeing here in the strong decreasing trend that we're showing in blue. And we, throughout the empirical analyses that we did, we benchmarked our evidential learning approach with the two leading epistemic model uncertainty estimation methods, being model ensembling as well as dropout sampling. So those are the two baselines that I'm going to show and highlight throughout this talk. And the key point, as you can appreciate, is that as we see increasing predictive confidences, we're also correlating with lower prediction errors, which shows that the method is calibrated to the underlying performance of the model. Furthermore, we can show that our approach can generalize across different data sets and different tasks in molecular property prediction. So as I showed on the previous slide, we considered protein ligand docking. We also considered biophysical properties like solubility, as well as quantum mechanical data, where here we're showing that, again, we're achieving strong calibration relative to the dropout and ensembling baselines. And a final class that we were really excited to benchmark and study was in sort of the low N regression regime, where in this case, low N is referring to data sets where we have fewer than 10,000 molecules. And across these different data sets and these different properties, we again see strong calibration. And so this confirms to us that our method is able to reliably capture relationships between uncertainty and predictive error. And to get in a little bit deeper into the heart of why this is because our evidential method provides this modular ability to tune and optimize calibration performance due to this regularization term that we incorporate into the loss function. And so if you recall from that prior slide, we have this two-component loss. The first term being the negative log likelihood, which maximizes the model's fit to the data, as well as this regularization term, where we're seeking to minimize evidence in instances where the model is making errors. And this is a notion of regularization. And as you can appreciate, right, we're introducing this, this parameter lambda, which controls the strength and the contribution of the regularization term. And we can see how this plays out in terms of the calibration of the uncertainties, namely that we can observe overconfident predictions when we are not reducing the incorrect evidence strongly enough, and furthermore, underconfident predictions when we are enforcing too great of a penalty when the model makes mistakes. So this intuitively means that we can treat this parameter as a hyperparameter to tune and optimize directly to try to achieve better calibration with our approach. We can see this play out empirically on a data set of molecular solubility, where we can see the effect of tuning this regularization parameter lambda. And when we benchmark against the calibration of our method relative to ensembles, we see performance that is at least as good in instances with the optimal value of the regularization coefficient lambda. I will also highlight on this slide that plenty of other recalibration or calibration optimization methods exist for uncertainty estimation in regression in particular. And the difference with our approach is that we introduce this, this parameter that can effectively be tuned directly as a hyperparameter. I believe I saw a hand raised. Yes.
Yeah. Can you just remind us of what phi of m was there in previous slide in phi function? Can you go to back slide?
Okay, let's see.
Yeah, here. Y minus expected mu into phi of m. Phi of psi.
I see. So this is I should have made this explicit. This is what is called the total evidence, and this is dictated as well by the parameters of the evidential distribution. And so if you look into the details of our paper, both the original NeurIPS 2020 paper as well as the ACS paper that shows the bulk of the results I'm presenting, that formulation is explicit. I believe it's alpha plus 2 mu that constitutes this this term phi of m. The intuition is that it's a metric of total evidence, and this is grounded in some background theory with respect to the evidential formulation itself.
Thank you.
Awesome. Okay, so hopefully that goes through the details of the evidential learning algorithm and how we have now developed molecular property prediction networks that can incorporate this algorithm to achieve uncertainty-aware molecular modeling. And so for the next portion of the talk, I'm going to focus on these two downstream applications by which we can deploy these uncertainties to accelerate experimental labeling and later to guide targeted virtual screening. Specifically in the case of efficient experimental labeling workflows, we specifically set up an active learning experimental regime where we can now deploy these uncertainties to guide the active learning process. Making that explicit, right, we consider a library of small molecules, we train a model to estimate properties and uncertainties, and use those estimated uncertainties to progressively acquire new sample batches, which are then annotated according to their true labels. And then this updated an augmented batch of samples is used to retrain the model and update the weights, and this process is repeated iteratively in this active learning paradigm. And so I'll showcase how we have used these evidential uncertainties to both improve sample efficiency as well as to accelerate the discovery of high-performing compounds. So first, considering the traditional active learning regime, where we're looking to accelerate sample efficiency in training. Here we're looking at a data set of organic molecules and their physical properties. And as you know, within this active learning paradigm, we can consider how well the model performs as a function of new data acquisition. And we see that even if we're selecting new data points at random, more data leads to more improved performance. But now if we instead use our evidential uncertainty to select new data points, we see that we can significantly cut down on the amount of data that's required to reach the same level of accuracy compared to the random sampling baseline. Furthermore, we observe that our evidential method can significantly outperform the dropout-based baseline and performs close to the level of the ensemble-based section. Again, highlighting that in this active learning regime, ensembling requires retraining multiple models at every iteration through the active learning experiment, whereas our method requires training just a single model and performing a single forward pass through the network to obtain these estimates of uncertainty. Quantifying the degree of improvement that we see, the evidential selection approach achieves a significant gain in the efficiency of this data acquisition process, right, where we see close to 20% improvement in prediction error at a fraction of the full training data. And this highlights that if we think back now to the experimental setups that ultimately we'd want to deploy our models in, what this means is that instead of having a human or a labeler go out and collect an entire training set, we can use these uncertainties to guide the selection of training data points that would be most informative to the model, and therefore achieve a level of high performance from a reduced fraction, only 20% of that experimental data itself. Similarly, we can now consider not only thinking about how uncertainty-guided acquisition can improve sample efficiency, but also whether we can couple those uncertainties with the predicted properties itself to try to guide the acquisition and search towards compounds that have desired molecular properties. This is specifically what we did in the context of Bayesian optimization, where now we're incorporating both the predicted property values as well as the estimated uncertainty in our data acquisition function. And we can see, right, if we just perform an absolute brute force search, considering exploration of a chemical space at random selection, that the rate at which we're able to discover the highest performing compounds, meaning those that have a target property of interest, is incredibly slow. In contrast, right, when we now start to incorporate evidential uncertainty into the acquisition, we can significantly improve on this baseline, rapidly identifying high-performing compounds at the level of the gold standard uncertainty quantification methods. Furthermore, now if we consider not only the ability to identify these compounds, but actually consider what their constituents are of these selected pools, we see that with evidential uncertainty, we can achieve a boost in the molecular diversity across the samples that we've selected, which is encouraging, although I think it remains to be validated how important this, how significant this level of increase actually is in a downstream application. All right. So for the last application, which I think is the most exciting and most relevant one, I'll share how we have actually deployed these uncertainties in the context of virtual screening to facilitate the discovery of high confidence molecular candidates. And our setup here was pretty intuitive, right? So far, we talked about how these uncertainties are formulated and how they can be deployed iteratively to improve sample efficiency during training specifically, right? Now, we were actually concerned with this question of whether these uncertainties would be useful at deployment to now facilitate the discovery and screen of high-performing and high-confidence molecule candidates that would have actually greater likelihoods of succeeding in the real world, right? And so we designed a pipeline where we hypothesized that we could learn a model on a small labeled data set for which we had experimental data, then apply it to an independent discovery data set, generate both property and evidential uncertainty predictions, and then take the resulting predictions of uncertainty to now not only rank candidates by their predicted property, but also to apply this confidence-based filtering to try to prioritize drug candidates for experimental testing and experimental validation. The underlying idea here is that this prioritization could guide our search towards compounds that would have greater likelihoods of experimental success. For our empirical analyses, we specifically focused on the task of antibiotic discovery, where we considered the urgent need for the discovery of new antibiotics, and also had at our hand an experimentally validated data set of candidate compounds tested for their ability to kill bacterial strains in the lab. And this was what we used as our training data set, small experimentally validated data set, and then trained an evidential model to both predict antibiotic activity and associated uncertainty. We then took that resulting model and applied it to an independent drug repurposing data set and considered the nomination of candidates based on both these two outputs. And so if we look at the spread and the distribution of that training data itself, you can notice a few things that I'll highlight now and hopefully will be good points for discussion as well. Firstly, that the data set is relatively small, right? It's only 2,535 compounds. And secondly, the balance of this data set is not there, right? It's quite skewed in that we have many, many more compounds that do not have significant antibiotic activity and fewer compounds that have actually potent inhibition. And this, I think, highlights a lot of opportunities for future work, and happy to talk more about the limitations of this data set and therefore how that affected our downstream analysis. But just to paint the picture, this is what we were working with, and this was what we used to train our model. So after training our model, we then deployed it right on this drug repurposing data set. What we found was that when we visualized the prediction uncertainties across this independent discovery data set against the chemical space mapped by our training data, we see that there are regions of the space that were less populated by the training data, but associated with higher evidential uncertainties as predicted by our model, right? Encouraging that we're actually able to identify and learn some of these underlying disparities in the data landscape. Now, when we actually performed the experiment of this guided prioritization, we consider the top-ranking molecules based solely on their predicted activity, and then calculate how many of those top-ranking candidates turned out to be true experimental hits in the real-world biology lab. And you can see that if we do not incorporate this uncertainty-based baseline, we're at this baseline level of experimental success. What was really exciting was the fact that when we now actually prioritize candidates based on these predicted uncertainties, we can significantly improve the real-world experimental success rate, moving to above 90% in this strong blue line, depending on how strictly we threshold this confidence-based prioritization. And so this really emphasizes this fact, at least in this setup and in this first experimental and empirical analysis, that by incorporating this uncertainty-based filter, we can start to think about how we can prioritize drug candidates with greater likelihoods of real-world success. And so to conclude, today I've showed you the details of our scalable and modular algorithm for uncertainty quantification in neural networks and how we can leverage that for molecular property prediction. And most importantly, how we can not only take those uncertainties, but actually deploy them forward to both improve the experimental labeling process, as with active learning, and actually guide the prioritization of high confidence drug candidates in the context of virtual screening. More generally, I think this provides just one example in molecular modeling and drug discovery of how we can think about achieving this dynamic and iterative dialogue between experimentation and computation. To that end, we have several projects that are ongoing in this space, more systematically thinking about how we can move these uncertainties forward to prospective experimental studies, and furthermore, how we can continue to develop the method on the fundamental front to achieve and meet the needs of tasks in the molecular and biological sciences. So with that, I will gratefully thank those who contributed to this work and the amazing team that I showcased the work today. And specifically, I would like to call out that our code is available. We have a paper published, and furthermore, that I'm always available and happy to discuss further by email. So please do reach out. Thank you so much for your attention, and happy to take any remaining questions in the remaining time.
Perfect. Thank you so much for the great presentation, Ava. There was a few questions in the chat. Maybe you can start with those, and if there's more time, we can take more questions.
Okay, so the first question, is a neural architecture necessary? Could uncertainty methods be applied to, e.g., to recursive partitioning? Great question. So absolutely, with non-neural approaches, there are a number of methods to think about uncertainty quantification in that context. For example, with random forests and decision tree methods, you can also generate metrics of uncertainty. In our context, with the evidential deep learning framework, we specifically focus on neural settings in which neural architectures are used. And furthermore, it kind of speaks also to the motivation behind the formulation itself, in that when deploying these large models, we really want to think about what would be a scalable way to estimate the model uncertainty directly, which therefore goes back to this motivation of trying to alleviate the need for ensembling or different types of approaches that require sampling. Another question, did you use typical ensembles or batch ensembles for the comparison? And by dropout, do you mean Monte Carlo dropout? Fantastic question. So at this time, we focused on traditional ensembles. I believe, yeah, the batch ensemble method is really cool, I will say, and we haven't benchmarked our approach against batch ensembling, but definitely that would be a relevant comparison in new studies going forward. And yes, dropout is Monte Carlo dropout in this setting. Can we say that this method is a variational inference-based uncertainty quantification? Interesting question. I personally have not thought exactly about likening it to variational inference approaches. I would say not exactly, no. The idea is that it is a distribution-free method, right? And by distribution-free method, I mean we don't require an approximation of the distribution that is generated by ensembling or dropout sampling, for example. The closest relationships, I would say, with our method are to mean variance estimation, and as was discussed earlier, the likening to Bayesian neural network approaches with the distinction that we're not parameterizing distributions over the network weights themselves. And then the final question that I think was not answered live was, will the distribution parameters have their own uncertainties? Interesting question, and this is kind of like a meta level point about whether or not you could formulate yet another higher order distribution on top of the evidential distribution. Yes, I guess, you know, in the sense of this being, there's always going to be some notion of uncertainty, regardless of what you formulate the prediction as. I think one challenge there, if you were to keep doing this hierarchy, is the limit at which it no longer becomes practical to train the model and to do so stably. And so we find, even with extending to the multivariate setting, where now you're predicting variances, a covariance matrix, and also the formulating then the variance relationship between the different outputs of your model in terms of that covariance matrix structure, that already becomes progressively more complicated versus the univariate setting. So I think in theory, you know, to go back to the stats and math of that would be interesting, but there's going to be a significant trade-off with respect to the practicality and the stability of actually formulating that and getting that to work stably.
Thank you so much, Ava, for answering this question. Do you have time for one more question?
I can do one more, and then unfortunately, I do have to go to another meeting.
Okay, thank you. So, so in some of the results you shown, like it was clear that evidential deep learning has better uncertainty estimation than ensemble method. But when it comes to active learning and Bayesian optimization, it was not always clear that it's actually have better active learning or better Bayesian optimization. So I was wondering, because we all have this assumption, better uncertainty mean better active learning and better Bayesian optimization, but something is missing. So just want your thought on what that thing missing to translate better uncertainty in better active learning and Bayesian optimization.
Yeah, I think it's a great question. I think part of the reason that we saw such strong performance with respect to the calibration was the fact that we have this regularization term incorporated into the objective, right? Which is explicitly trying to minimize the incorrect evidence on errors. And then in the active learning setting, we saw comparable performance across the three methods. You know, I think that it's hard to say. I think that being also from having experimental training and background, my opinion on what is the real metric and bar for what is more performant is how well the method does in a prospective setting where you actually go out and take those predictions or that active learning output and deploy it in the real world, right? I kind of framed the talk in that way, but these analyses largely were in silico context set up in that way. So firstly, I think that precedent needs to be better established. In terms of the methodology itself, I think my intuition is that a method that is better suited at looking at identifying what is truly an out of distribution instance and being calibrated to that would be more performant in the active learning setting when we think about a purely explorative selection. Whereas the calibration results I showed were considering the correlation of confidence with predictive error, right? Which is not exactly the same thing. So thinking through some of what these exact benchmarks are going to be, I think will be important as well. And on the methodology front, I think to the earlier point, looking at some of these emerging approaches will be interesting as well to see how well they perform in these types of settings.